Okay, so let's look at an example where we mix two gases. So each has their own pressure and volume starting, and then we mix it to make one big mixture of gases. And we see how that happens or what effect that has on the total pressure of the system. Okay, so in this specific example, we're told we have a flask containing nitrogen gas, a certain volume and pressure, and a flask containing hydrogen gas, a certain volume and pressure. And it's connected, these two flasks are connected by a valve, and the valve is then opened, and we can assume that there is no change in the temperature, of course, also in the amount of the gas, of the individual gases. And then we're asked to determine the total final pressure or the total pressure of the final mixture. So what this looks at is what is the relationship between pressure, number of moles, temperature, and volume. So there are two things that remain constant and two things that change. We'll have initial pressures, and which leads to a final pressure. We'll have initial volumes that will lead to final volumes. But the number of moles of gas, so at the beginning, and the temperature of the system at the beginning remain constant. So these are constants. And that means we can use specific kind of equations, which we can introduce, or which we'll look at just now. But let's draw a picture of what this scenario is. So we have a glass bulb system, something like that. And this has a stopcock. I don't like that. Beforehand. So at the start, we have some nitrogen gas on the one side. We're told the volume of the nitrogen gas initially is equal to 3 liter. And we also are told the pressure of the nitrogen gas initially, and that is equal to 1.80 atmosphere. And then we have some hydrogen gas on the other side. So this is hydrogen gas. And we also told some information about that. So we have an initial volume of hydrogen gas, which is equal to 2.00 liter. And we have a pressure of hydrogen gas in that bulb initially of 1.8, 3.5 atmosphere. Okay, so that's our initial picture. We have two things that are separated, and we can see them as two systems apart, each where the pressure of the hydrogen is the pressure of that bulb because there's only hydrogen in it, and the pressure of the nitrogen one is the total pressure and the total volume, and that is what it is. So then we open the stopcock, so we open, and that then of course leads to a mixing of the gases. So if we, yeah, that's really bad. I sometimes actually just do this. I should have done that from the beginning. Yeah. Um, so then once we've opened that thing, the valve, we see that the nitrogen, spreads equally throughout all of these. That's because of entropy, but you don't know that yet. And there will be some Gibbs energy dictating which one goes where more. But we have a mixture now. So now, what does blue and green make? I think it's purple. Makes purple. So we actually have nitrogen gas plus hydrogen gas in this case. All right. What is the thing that changes that is more important? So we no longer have two separate volumes, we now have a final volume. So the final volume of this system is equal to the initial volume of the nitrogen plus that of the hydrogen. Hydrogen initial, and that is of course equal to 5.00 liter, because both gases now have access to the full bulb or the full part of the flask, so whatever you want to call it. The question is now, what is the total pressure of the final mixture? So sort of what is the PF? We can call it PF total. That's not in line with the way that I wrote the notation thus far. So it's P total F. P total at the end. Can we just say it is the sum of the two partial pressures at the beginning? Of course, no. And the reason for that is because there is a volume change. There's a change in volume. So we can't just say the initial pressures in two different volumes now sum together and that gives us our final pressure, because we still have the same amount of gas, but in principle, their volume has increased. So there's some adjustment according to the pressure. So we need to determine a way of doing that. But we do know what it would be. The total pressure would be equal to the partial pressure of the nitrogen gas after mixing plus the partial pressure of the hydrogen gas after mixing. And we have enough information to determine what the partial pressures are of the gas after mixing. So that's what we want to determine. We want to determine the two partial pressures so we can sum them and get the final, the total final pressure. And so if we think about the ideal gas equation, PV is equal to nRT, when N and T, or when two of them are constant, when N, T are constant, we know that we can relate these quantities in some manner. So, of course, R is a constant, and T is a constant, and N is a constant. That means the product of P times V, that means PV must be equal to a constant value. Hence, we can say that the product, so pressure times volume of some initial situation must be equal to the pressure times the volume of some final situation. And hence, we get to an equation of the form P1 V1 is equal to P2 V2. All right, so that's the origin of that equation. But you can logically deduce it. You don't need to know that that's the equation. So what does P1 V1 mean equal P2 V2 mean in this case? So for example, for nitrogen, it means that the partial pressure of nitrogen initially times the volume of nitrogen initially will be equal to the partial pressure of nitrogen after mixing times the volume of the final mixture. So just F, because there's no volume for nitrogen and volume for hydrogen still, it's now just the total volume. And what are we interested in? We're interested in the partial pressure of nitrogen at the end, so the final one. So therefore, the partial pressure of nitrogen in the final state is equal to the partial pressure of nitrogen initially multiplied by the volume of nitrogen initially divided by the final volume. And these values are, the initial pressure is 1.8 naught atmosphere. The initial volume is 3 liter. And the final volume is 5 liter. And you can sort of see that this is a volume ratio. So we take the initial pressure and it's multiplied by the ratio of the volume. So 3 to 5, the volume was increased by a bit. So it went from 3 to 5. So in other words, we multiply by that fraction and then we get what the pressure change would have been. That makes a lot of sense. If the volume is increased by, what is this, 2/3, then in other words, the pressure should decrease by around about that amount. So we get here 0.8 atmosphere, some numbers atmosphere. In a similar fashion, we can calculate the pressures of the hydrogen. So it will be the partial pressure of hydrogen initially multiplied by the volume of hydrogen initially is equal to the partial pressure of hydrogen in the end multiplied by the final volume. So the partial pressure of hydrogen finally is equal to partial pressure hydrogen initial, volume hydrogen initial divided by the final volume. And these values are 3.50 atmosphere, 2 liter divided by 5 liter. And again, you see that ratio of the volume. So initial volume to final volume multiplied by the initial pressure is what dictates the change. But that is only true when the number of moles of gas and the temperature of the gas remains constant. If the temperature changed, then we would have had a different factor at play here. Anyway, here you'll get a value of 101.04 atmosphere. Right, and then we just sum that. So therefore, the total pressure of the system after mixing, which is also the final pressure, is equal to the sum of the partial pressures after mixing. (2.48 atmosphere). 3 significant figures. Or 3 significant figures, but we summed 2 things, so we're looking for 2 decimal places. That's the important thing. Anyway, what did I want to say now? Oh, I wanted to compare the sum. So for example, if we just summed the initial partial pressures, we would have gotten a value of 5.3 atmosphere. And of course, there's 2.48 atmosphere is much less than that, because what you did not take into account is the volume change if you just sum the initial partial pressures. Okay, I hope this one was a nice example of how the volume changes the pressure of something. And I kind of like these kinds of questions. I like the little bulbs. I hate drawing them, but I like thinking about them. Anyway, thank you for watching. I hope this was insightful.